All right, in section 13, we'll be looking at trigonometry. This is one of the sections students tend to like less, with good reason. There's a lot of, I wouldn't say memorization involved, but things that look foreign, but really aren't, like pi. As you can see here, the picture, sine, cosine, functions like that. Anyway, let's get started. It should be review most of it, but again, if you're learning it for the first time, no big deal. First things first, the unit circle. The unit circle we deal with a lot in trigonometry. The unit circle we need for, well, just about everything in trigonometry. And here we could see what it looks like, right? So there are two things. One's in degrees and it's in radians as well. So I write it up here. There's degrees and there are radians. And then these over here are the x coordinates and the y coordinates. So, and if you remember, these coordinates, x and y, cosine was always the x, sine was always the y. With that said, we could go ahead and fill in this little table here, or these values. Find the following values. Cosine of pi over 6. So let me go ahead and erase this. Cosine pi over 6. What is that? So we identify pi over 6, and then we remember cosine is always the first one, the x value. So cosine pi over 6 is square root of 3 over 2. That's all that is. Next one is sine pi over 6. So again, we'll be at pi over 6 here. But now sine is always the second one, the y value. So this one would be 1/2. This is how we can fill all these out. This one here, 150 degrees. It's not giving us the radians, it's giving us the degrees now here. And sine is always the second one, the y value, so that one is also 1/2. So we could go ahead and fill all these out. Cosine 2 over 3, that's over here. Cosine is the first one, that's negative 1/2. And I'll just fill the, actually this one gets a bit more interesting. Sine pi over 7 pi over 4. That one's right here. Don't let it trick you. They're mostly all in the unit circle. You can find this one here. Negative square root of 2 over 2. The one that gets tricky is this one. Tangent, if you remember, is sine over cosine. And it's pi over 4, since we have pi over 4, and pi over 4. Sine pi over 4, square root of 2 over 2, over cosine pi over 4, which is also square root of 2 over 2. That'll equal just 1. I sped through these mostly because it's just identifying where everything is on the unit circle. Something you might have learned in geometry, they probably went through it thoroughly, is Socatoa. If you remember Socatoa, we use it when dealing with right triangles, meaning there's a right angle, an angle of 90 degrees. If you remember, the rules for Socatoa were the following. Sine of the angle theta would be opposite over hypotenuse, cosine would be adjacent over hypotenuse, and so on and so forth. And if you don't remember, we can go ahead and do an example. So let's say we're given this triangle here, this right triangle. Given the triangle, find sine theta and secant theta. So in this case, theta is right here. And sine, they're telling us, is opposite over hypotenuse. So what's opposite of theta? Opposite of theta would be 6. So 6 over hypotenuse. And hypotenuse is always the longest side. The slant, 10. Right, so that one would just be 6 over 10. Or if we reduce it, we simplify it, it is 3 over 5. Same thing with secant. Secant, now we just have to look at this. Hypotenuse over adjacent. So that would just be 10 over 8, or if we reduce it, that would be 5 over 4. That's Socatoa. how to deal with right triangles, how to find, the angles or the sine function, cosine, all the trigonometric functions, how to find their value given a right triangle. Next thing, probably what made students hate trigonometry the most are trigonometric identities. What we do with identities is we pretty much solve a puzzle. We simplify expressions using these identities. And for example, if they ask us to simplify the expression cosine t plus tangent t times sine t, well, we see that, and a lot of us are, deer in headlights, right? We're like, okay, what do we do here? What am I supposed to do? A lot of the times it's just looking at the trigonometric functions. There's one for cosine. Actually, not here. There isn't one for sine either. So, basically the clue here is tangents can be not expanded, but rewritten as sine t over cosine t. So this tangent got rewritten as sine t over cosine t. And to add these two, well, first things first, we're going to want to multiply sine t times sine t for that fraction. But to be able to add these two, because we have an addition right there, a sum, we're going to have the same common denominator, right? This fraction has a denominator of cosine t. So what we're going to have to do is multiply this cosine t times cosine t over cosine t. So that's going to look something like this. So notice over here we have cosine t squared because we have 2 now over cosine t. In other words, we did cosine t times cosine t over cosine t plus, and then what was left, sine t plus cosine t times sine t. And right here we got cosine t squared over cosine t, and then the rest over here. And now we do that because we now have a same common denominator. Right, so that now we can combine the fractions and we have cosine squared t plus sine squared t over cosine squared t. Now, if you're used to working with problems like these, you can already recognize what this is equal to. If you're not familiar with it, go ahead and look at the Pythagorean identities up there on the chart. And you'll notice that that is actually equal to 1, just 1. So that is just equal to 1 over cosine t. And the last thing to do is if you look up at the chart again, right here, 1 over cosine x is the same thing as secant x. So our example just becomes secant t. So that might be crazy, we simplified this whole thing, and this whole thing just equals secant t using our identities. And this is a puzzle because you need to figure out what can replace what, so you're able to simplify the expressions. We'll do one more. If you want to try it on your own, you can go ahead and pause the video here and go ahead and try it on your own. I'll give you a hint. You do need the same common denominator here. So I'll give you that hint, and it might get a bit messy, but it cleans up nice. So let's go ahead and see. We're going to need the same common denominator. I'm going to skip a step. To have the same common denominator, I'll give you the step here. You have to multiply both of these. These two multiplied and these two multiplied. So we can have on the denominator 1 plus sine x times cosine x, and then over here cosine x over cosine x. Oh, sorry. There we go. That's a step I'm going to skip, and I'm just going to write it like this, as a fraction already combined with the same common, or with the denominator. Once you do that, we can go ahead and distribute here. Sine x times 1 is just sine x. Sine x times sine x is sine x squared. Or sine squared x plus cosine squared x. And just like in the last problem, we have something we can recognize here from the Pythagorean identities. That becomes sine x plus 1. Now notice we have the numerator and the denominator, we have the same thing. I'm going to put these in parentheses. We can now cancel these two out, right? They're the same thing. What are we left with? 1 over cosine x, which is, again, like the last problem, secant x. So we just saw two other different ways of writing secant x, right? With all these identities, we were able to figure that out. This over here was secant x, this over here was secant x, or just secant x. So that's the identities we tend to deal with. It really is just like puzzles. That's why people don't like them. A lot of the times we don't know if we're doing this correct. We're taking the correct step because of the fact that sometimes it looks messy, like that step, this step. They look a bit messy, you know, but then they clean up nice. All right, this video is one of the longer ones. If you want to take breaks, it's not so easy to stay focused on math the same way it is to stay focused on a TV show or a movie. So if you need a break, just go ahead and take a break. We're going to be moving on to cosine curves. And mostly just how cosine and sine curves, what they look like. So we're going to go ahead and sketch each graph and describe the transformations. So let's say we're given these two functions. 2 plus cosine x. We'll focus on this one first. I'll give you the visual. The original equation, cosine x, is the one in blue. This new modified one is in red, 2 plus cosine x. Notice, all it did was it shifted the blue graph up 2 units to become the red graph. And that's what this number 2 here did. The plus 2 shifted our graph 2 units up. And I believe over in lesson 10, yes, lesson 10, we went over quadratic functions. Not in detail, but we went over the transformations, how they change. These are really similar. The plus 2 shifted it up 2 units. Now the negative over here, what is this negative going to do? I'll show you what it does. The negative is now in red. Now it looks like a double helix, but what happened? What happened was having a negative on a trigonometric function or on a cosine and sine, it'll reflect it across the x-axis, right? So the x-axis acts as a mirror and the function gets reflected. That's just some other transformations, kind of showing you just how they relate to the quadratic function transformations. They really are two of the same. It's just, quadratic functions are a type of polynomials. These functions are not polynomials, they're trigonometric functions. All right, now we can take a look at sine curves. I'm going to show you what all these functions look like. What happens if we put a coefficient, meaning a number in front of the function sine? We have the one in blue, y equals sine x, our regular function. We have the one in black, which is 1/2. We have 3, and then we have a negative number, which we know reflects it. So let's go ahead and take a look at how these look. So I've labeled all these for you. Notice what happens to them. Notice the one in red, it's a coefficient of 3. The bigger the coefficient, the taller or the higher and the lower that it goes. And we call that the amplitude. We'll go over that shortly. The 1/2, because it's less than 1, it's a bit more, like compressed. Yeah. And then the one in orange, that's a negative, so that one got reflected. So just like I had mentioned, when you have a function sine x or cosine x and there's a coefficient a in the front of them, the absolute value of that number, a, is what we call the amplitude. So the function in black has amplitude 1/2. This one has amplitude 3. This one has amplitude 2. Remember, we take the absolute value, right? So absolute value of 2 is 2. Negative 2 is 2. So if they were to ask us to find the amplitude of a negative 3 cosine x, we know to take the number in front, take the absolute value of it, and that gives us 3. Now, how would that look if we graphed it? Well, because it is negative, instead of starting at the top over here like cosine usually does, we'll start at the bottom because it gets reflected. And that'll look something like, I'm going to try my best to draw this. It'll look something like this. From here, we keep going on, so on and so forth. So this is amplitude. What's next is what we call the period. And this is actually the last slide. The period of a sine function and a cosine function is usually just 2 pi. However, that can change, but let me show you what that period looks like. The period here for cosine x and sine x is 2 pi. The reason it's 2 pi here is basically when it restarts, when the pattern restarts. So it starts here, goes on a little down, it goes downward and then up. Once it reaches 2 pi, notice how the pattern starts all over again. We go down, up, and then 4 pi, it'll start all over again. So on and so forth. That's why there's a period. We call it a period because it repeats. So 2 pi. Sine starts at 0 at the origin usually, or yeah, sine t will start at the origin. And the period, well, the function goes up and then down, and then right here at 2 pi, it'll start again. Up, down, and right here it'll start again. Careful. I've seen a lot of students think the period is pi because they think, well, we reach this point again, 0. This is the period. But it's not. You haven't even gone down yet. You have to go all the way down again. And then once you reach 2 pi, now you can start the pattern all over again. So just careful with that. I'm going to show you what happens if we add a number in front of the x, sine 2x. What happened now? The period got shorter. And if we add 1/2 instead of 2, the period got longer. In this case, the 2 made it more frequent, right? So it's frequent. The period in this case, I'll give you a spoiler, period is pi instead of 2 pi. But in this other case, you can go ahead and take a guess. The period is 4 pi. Notice how it goes up and then down, and then once we get to 4 pi, it starts repeating again. So that number in front of the x can change it. And these waves, if you ever studied physics or seen anything dealing with the electromagnetic spectrum, you see that gamma rays have the highest frequency, look something like this, where the period is incredibly tiny, and then there's radio waves on the other side of the spectrum that are huge, where their periods are a lot longer. So because gamma rays and X-rays have way higher frequency, they carry a lot more energy, and that's why they are so dangerous to us. Whereas radio waves don't carry nearly as much energy, so that radiation hardly affects us. So a lot of information. The one thing to do keep in mind is this table. Shifted, sine, and cosine. So right here, amplitude, remember, is always A, this number right here, this number right here. Period, to find period, you'll get this number here, the K, and you'll put 2 pi over that number. And that'll give you your new period. And then B, inside the parentheses, if we were to have, if you look down here, on the sine function, if we were to have a parentheses here, -4, that would have been a horizontal shift. All right. That concludes these transformations, like I said, really similar to polynomial transformations. And as far as trigonometric identities go, that's probably the tougher section. After teaching it over and over again, I start memorizing it, but, learning it for the first time, you hardly ever memorize all of this the first time around. Hardly anyone does. So after this, we'll have 2 more lessons, and we should be done with the lessons.